Good morning, student. If we continue from the last part of the lecture, one can see the total amount of outward flux through the volume element in y direction. What will be its value? As I have already told, we have adopt the expression 1 as expression 2, and if we adopt these two expression, then this value will be equal to how much? Ay plus delta, fy plus delta f divided by delta y dy into dx dz minus fy dx dz. Okay, so this value will give us del fy by del y dx dy into dz. Okay, so this is the net amount of outward flux in the y direction of this volume element. Okay, so as I have already told, dx dy dz, this quantity is known as the dv, the value of the volume element. So we can write it as del fy by del y into dv. Okay, so this is in the y direction. Similarly, we can find out the value of the net outward flux in the z direction as well as in the x direction. So in z direction, what will be its value? As you can see, so in the x direction, del fy by del y into dv. So in the z direction, it should be del fz by del z into dv. So this is 1, so this is 3, so this will be 4, and in x direction it will be how much? Del fx by del x into dv. So this is equation 6. Okay, so now if we have to find out total amount of outward flux through this whole volume element, so what we have to do, we have to add up simply 3 4 5 and 3. Okay, so the net the total outward flux through the volume element, what will be its value? You have to just add up this 3 quantity. Okay, so I start in that fashion, x, y and z. So it will be like del fx by del x plus del fy by del y plus del fz by del z. Okay, into dv because this is nothing but, and dx dy dz is nothing but dv. So we have to sum up these three things into and multiply by dv. Okay, so this quantity del f by del x plus del f by del y plus del f by del z is equal to what? Nothing but the divergence of that vector field, which I have already discussed many times. Okay, so del dot f into dv is equal to total outward flux through the volume element. Okay, so from this expression, one can easily understand what is the physical significance of that divergence of the quantity. So divergence of a quantity or divergence of any vector field is what is now what? The total outward flux per unit volume of a the total outward flux per unit volume at each point in that vector field. Okay, so del dot f, from this expression one can see del dot f is equal to this thing divided by dv. Dv is the value of that volume element. Therefore del dot f physically represent what? That net, and del dot f is nothing but the total outward flux per unit volume at each point of that vector field. So this is the physical meaning of a divergence of a vector field. Okay, so this divergence of a vector field, you will find you'll find many example of divergence of a vector field in electrostatic as well as in magnetostatic. So for example, Gauss's law is nothing but the divergence of an electric field. And if you remember the the differential form of Gauss's law, then it was del dot E is equal to rho by epsilon naught. This is the statement of Gauss law in a differential form. So the divergence of an electric field is equal to rho over epsilon naught. Here the divergence of the electric field means the total flux of electric field per unit volume, and the per unit volume, and that is equal to rho by epsilon naught. So this divergence quantity has a physical meaning, and it represents the total outward flux of any vector field per unit volume in a region or at any point of that vector field. So you have to remember this this definition or this physical meaning. Okay, so in the next class I'm going to discuss another meaning of another very important vector operator which we have already discussed, and that is the curl of a vector field. Okay, so in the next part of the video we are going to find out what is the physical meaning of a curl of a vector field. Okay.